Gases are definitely unique in that they can be compressed. They're not like solids and liquids. So when we're talking about like the density of gold, a solid, it's always the same number, no matter what the conditions are, like the temperature, the pressure. But for gases, what we could do is, we could have a certain gas like in a certain volume. Like we'll put a gas in a box here. So we have all these gas particles floating around in this box. But what we could do is we could put some pressure and shrink this box down to a smaller size. And all the gas particles, or the mass, would still be in it. So then even though it's the same gas, as it went from here to here, it would become more dense. So the density can be almost anything depending on the temperature and the pressure conditions. So when we're talking about densities of gases in these next couple problems, it's important that we understand that I'm going to give you three densities here: gas A, gas B, and gas C. But I need to also give you conditions. So these conditions here would be at STP, which means standard temperature and pressure, which basically means 273 Kelvin, or 0 degrees Celsius, and 1 atmosphere of pressure. And we know at STP, we happen to know at STP some important information, and that is the molar volume of a gas, which means at STP, only at STP, 1 mole of any gas, doesn't matter what kind of gas it is, will equal 22.4 liters. It will be in a volume of 22.4 liters. So it's very important to be able to know that particular volume. So I gave you three densities here of gas A, gas B, and gas C, and we need to figure out what these gases are. We want to try to name these gases. To be able to classify these gases, we of course need to be able to figure out their molar mass. Right now we have their densities, and we want to be able to figure out their mass, their molar mass. So at STP, we actually know the volume. So if you remember, there's an important equation a long time ago about density, and the way we remembered that was we said we love density. So density was mass, there's an M right there, over volume. Density equals mass over volume. So I'm saying that these gases are under STP, and because they're under STP, that means I can call this density the density of 1 mole. I know the molar mass is grams per mole, so the mass would be per mole, and the volume of 1 mole is 22.4. So I actually know the density and the volume for these gases. So to figure out the molar mass is very simple. All I need to do is take density times the volume. Density times the volume would give me the molar mass. And that's what we're going to do on this page. But first of all, I'm going to give you a list of gases to choose from for these three gases. So we're going to find the molar masses of these 5 gases. So you might want to pause the movie and try to write the formulas for all these, and then we'll see if you're right. I'll go ahead and start. So the formula for ammonia is NH3. Remember, this is different than the ammonium ion, which is NH4+. This is actually a compound. This isn't an ion. So it's ammonia. Sulfur dioxide is kind of like it sounds. Chlorine gas, remember, is diatomic. So is nitrogen gas. And methane is the simplest hydrocarbon we can have. So a carbon, and a carbon, remember, makes 4 bonds, so it would be CH4. So if I add up the molar masses for these, ammonia, nitrogen is 14, and then each hydrogen is 1, so that'd be 17 grams per mole. Sulfur is 32, oxygen is 16, so it'd be 16 times 2 is 32, and another 32 would be 64. Chlorine is 35, but it's diatomic, so it'd be 70. Nitrogen is 14, but it's diatomic, so it'd be 28. And carbon is 12, and 4 hydrogens of 1 each would be a total of 16. So here's our molar mass. These are all, by the way, in grams per mole. So these are our molar masses that we're going to choose from and try to figure out which gases are which on the previous page. So let's go back here and let's figure out the molar masses. And the way we can do that is take the density times the molar volume. So each of these, I'm going to take 1.25. And if I want to show it dimensional analysis wise, I can still put my units, grams per liter. And then that's my density. I'm going to take it times the volume, according to this, times 22.4 liters, see? And that actually would be liters per 1 mole. And so my liters would cancel out. My units are in grams per mole, which of course is the units for molar mass. So if I do the math on that one, I get 28 grams per mole. And we'll check that out here. Let's do another one. Let's do 2.86 grams per liter is my density. And the molar volume is 22.4 liters for every mole. And liters cancel out. And if I do the math on that, I get 64 grams per mole. And the last one we have here, let's get some green here, 0.714 grams per liter. And there's 22.4 liters in every mole. Liters cancel. 0.714 times 22.4 is 16 grams per mole. So I have 28, 64, and 16. So if I look those up, 28, the first one is nitrogen, 64, the second one was sulfur dioxide, and 16. So the third one was methane. And I can classify all of those 3 gases because I know their densities, and I'm just going to assume in these problems, let's just say we have 1 mole. We can say we have any amount, but I can say, let's say we have 1 mole. So this would be the density of 1 mole of gas. The volume at STP, the volume of 1 mole of gas is 22.4. And the mass of a mole of a substance, of course, is the molar mass. So I end up using density equals mass times volume. I could easily do the reverse of this, and I could say, what's the density of, any gas at STP? For instance, if I said, what is the density of fluorine gas at STP? What's the density? Well, density equals mass over volume, right? So the density would be the mass of fluorine gas, the molar mass of fluorine gas, and fluorine's diatomic, and it's 19, so it would be times 2, it would be 38. So the density would be, the mass would be 38 grams per mole. And I would just take the molar mass and I would divide it by the molar volume, which would be 22.4 liters per mole. So I put 1 mole on top and my mole would cancel out. So basically I'm taking the mass, 38, divided by the volume, 22.4. And I could do that, 38 divided by 22.4, and I would get 1.7 grams per liter. That would be the density of fluorine gas. Now some of you might get confused a little bit and say, well, that's greater than 1, so why doesn't it sink in water? Well, it doesn't sink in water, obviously, because it's a gas, first of all. But the other thing is that these aren't the same units as the density of water. Usually the density that we use for water, so at 1 is grams per milliliter, not grams per liter. So technically you'd have to take 1.7 divided by 1,000 if you wanted to actually put in grams per liter, and that would be 0.0017 grams per milliliter. So if you want to compare to water, then you got to put in the exact same units. And clearly this is way less than 1, as all gases would be. The gases clearly are less dense than than water. But if you want to find the density of a gas at STP, just take the molar mass of it and divide it by the molar volume. And hopefully that helps you understand about the density of gases.